Chords of a circle, 7-2. Our objective for this section is define a chord, determine measures of angles formed by chords, determine measures of segments of chords. So a chord is any line segment whose endpoints are on the circle. Any line segment whose endpoints are on the circle. So we've got so you know, if I have a circle, all right, then a chord is simply that. That's a chord. It's a segment whose endpoints are on the circle. In how could I, in terms of a chord, how could I define a diameter? I can define it two ways. Ahija. Yeah, that's one way. We can say it's a chord that contains the center of the circle. Okay, how else could I define it? In terms of a chord, the diameter? Any ideas? Okay, it's the longest chord in a circle. We could also define it as the longest chord. Alright, any questions there? Everybody has it? Okay. Perpendicular bisector of a chord. The perpendicular bisector of a chord contains the center of the circle. So we have segment AB. Line L is its perpendicular bisector. It's going to go through the center of the circle. Here's a proof of that. So chord AB on the circle O. O lies on the perpendicular bisector of AB. Is what we have to prove. Our proof, Carmen, will you shut the door? Our proof, we could say, to prove that, you guys can draw this in on your figure. Is that AO and BO are radii. I'll draw it here so I can explain it. Let me draw the picture. So we have the perpendicular bisector. We know that AO and BO are radii, so they're congruent. So they're, and then if a chord AB of the circle O. So these two lines are congruent. This means that O is equidistant from A and B. Therefore, O is on the perpendicular bisector of AB. All right, simple proof. Okay, a corollary. So we didn't even need to know that. So really, I kind of went out of order on that proof. We wouldn't know these two things. We wouldn't know it's a perpendicular bisector, right? We would just know that we've got point O is the center of the circle. AO equals BO. We know if a point is on equidistant from the endpoints of a line, then it's on the perpendicular bisector. So that makes that line L a perpendicular bisector. A corollary to that, the intersection of perpendicular bisectors of any two non-parallel chords of a circle is the center of the circle. Right? So the perpendicular bisector of the chord meet at the center of the circle. Now this comes in handy if, let's say you don't have the complete circle. you've got a circle. So you've got a circle, you've got that much of the circle. For some reason, you know, this is like a plate or something that's broken off. That part's gone. We can still find the center of that circle. I would just draw two chords. I would draw two chords on it. Right? Construct the perpendicular bisectors. And they would meet at the, we know the perpendicular bisector of a chord goes through the center. We just defined that. So we could find the center doing that. Questions? Okay. Given two non-parallel chords, A and B, their perpendicular bisectors on them, prove that the lines intersect at the center. The proof of that. Because the chords are not parallel, neither are their perpendicular bisectors. Thus, the perpendicular bisectors intersect at one point. By Theorem 7.4, this point must be the center because both lines contain the center of the circle. Corollary. Two circles, O and O prime, intersect at the points A and B. The line containing O and O prime is the perpendicular bisector of AB. So this line is going to be the perpendicular bisector of AB. Alright, so we note the line such as OO prime connecting the two centers of the circle is called the line of centers because it goes through the two centers. So given the circles O and O prime intersecting points A and B, prove that OO prime is the perpendicular bisector of AB. The proof. By Theorem 7.4, the perpendicular bisector of AB contains the centers of both circle O and O prime. Thus, AB is a chord of each circle. The line of centers O prime is the perpendicular bisector of AB. Alright, so since AB goes, the O prime goes through both centers, AB is a perpendicular bisector in both circles. Okay, so then we would know that if it's the perpendicular bisector, then AB would this segment would equal that segment, and it's perpendicular. All right, any questions? Okay, put your phone away, Nick. All right. Show three different ways to construct a perpendicular bisector of chord AB in a circle with center O. So let's think about this. What's one way I could construct the perpendicular bisector? One way. Yes.
Find the center of AB and then connect that with central chord with O.
Yeah. Okay. Well, take it a step further. We could do the perpendicular bisector of AB construction. Remember, that's you go from A and B. For the perpendicular bisector construction, from A and B, you make intersecting arcs up here, intersecting arcs down here. You draw the line through, right? Or in other words, it's a fish construction. I think I taught you that as the fish construction, right? You do the fish construction, and that's going to construct the perpendicular bisector. What's another way I could construct the perpendicular bisector through to AB through O? Shatice.
Like you would measure, or like you would like make
we go on from AO and like line BO like that are equidistant, and then O would be on the perpendicular bisector of AB.
Yeah, that's kind of what we just did.
Oh.
These are constructions we know how to do. We've done these constructions. All these constructions, they have a name to them. You might think of another one. Okay, so this one would be the second one. We could do perpendicular from a point not on a line, right? That's the smile construction. We could do the smile construction. Smile and then intersecting arcs from the smile. And we draw the line. That's another way we can do it. Can anybody think of another one we could do? Okay, we could do the angle bisector. So we take line AO and OB, and this is the angle bisector. You're probably not as familiar with that one. The angle bisector on the angle bisector construction, we would do. So you would put an arc through the angle, and then from these 2 points, you make intersecting arcs, and then you draw the line, right? Angle bisector. All right, any questions there? Okay. Measures of angles formed by chords. Find the measure of AEC. All right. So to do this, I'll give you a clue. We draw in this chord CB. Okay? Now, how do you think we could find the measure of AEC? Any ideas how we could approach this proof? Any ideas? Okay, well, I know that angle B is half of arc 60, right? So angle B would be 30. So we have angle B equals 1/2 of 60 degrees, which is equal to 30 degrees. Angle C is 1/2 of 90, right? It's 45. So angle C equals 1/2 of 90, which is equal to 45 degrees, right? So now, how can I find AEC? Shatiz?
You could use triangle sum theorem to find angle CEB, and then use linear pair to find CEA or AEC.
Right, that's one way. He did that in 2 steps. How could we do that in 1 step? Yes? Now vertical angles. How about exterior angles? Right? Exterior angles. Angle AEC is an exterior angle of triangle BCE. Right? So it's an exterior angle. So then we know that in an exterior angle, the angle AEC is equal to angle B plus angle C, which is equal to 30 plus 45, which equals to 75. So it would be 75 degrees because it's the exterior angle. Any questions there? Okay. New theorem here. If two chords intersect, then the measure of any one of the vertical angles formed is equal to half the sum of the measures of the two arcs intercepted by the two vertical angles. So it is saying that we've got, if we angle AEC would equal to 1/2 the sum of this angle plus that angle, right? It equals 1/2 the sum of those two angles. And so would BED. And then we can do if we need to find AED, AED would equal to 1/2 the sum of AD plus CB. Which is angle BEC. This does not mean that arc AC must be congruent to BD. They don't have to be congruent. It's just the average of those two. Alright? And you can see from our example above, the 60 and the 90, if we added those two together and divided by 2, it's 75, and that's what we got for our angle. And so, we kind of proved that using numbers, but that's the case for all those. So if, like if this was 40, if this was 40, and this was 80, right? To find this angle, AEC, we would take 40 plus 80 divided by 2, which is equal to 60 degrees. All right, any questions there? Okay. Measures of segments of chords. If two chords intersect a circle, the product of the lengths of the segments, the product of the lengths of the two segments formed on one chord is equal to the product of the lengths of the two segments formed on the other chord. All right. So this says that AE times BE would be equal to CE times ED. Those two things, if I multiply them together, they will be equal. We're going to prove it. So we're given chords AB and CD. We had AB and CD. They intersect at E. We're going to prove that AE times BE equals CE times DE. So to do that, we're going to show that these two triangles, this triangle and this triangle, we're going to show that they are similar using corresponding parts. So we've got how do I know that AEC is congruent to DEB? Abby. Right, vertical angles. VA. And then we've got angle C equals angle B, which equals half of AD. How do we know that? Shatice?
The inscribed angle theorem?
Yeah, they inscribe the same arc. So it's not the inscribed angle theorem. The inscribed angle theorem says the inscribed angle is half the arc it intersects. This one, we're just saying that angles inscribe the same arc. And we know that from a corollary that they'd be the same, right? Angles inscribe the same arc. Step 3. What would step 3, what would I be saying there by angle-angle similarity? Zach?
Triangle AEC.
Yeah, triangle AEC is congruent to triangle DEB. That's true. Okay. So now, how do I know that AE, the ratio of AE to CE is equal to the ratio of DE to EB? How would I know that? Shatiz.
Corresponding parts.
Right, that's CP. Corresponding parts. And then what do I know by cross multiplication? Adhicha.
AE times BE equals
AE
CE.
times BE equals CE times DE. That's correct. And that's what we had to prove. All right. Questions on the proof? Okay. So this one has two parts to it. We have to find the angle AEC, and then we have to find the missing length EB. Let's find AEC first. How do I find AEC? Somebody besides Shatiz. And Adhicha. Somebody different. Lexi.
You add 40 and 60.
Right. So we have angle AEC equals 1/2 40 degrees plus 60 degrees, which is equal to 50 degrees. All right, any questions there? All right, how about finding EB? How would I find EB? Ben?
You would take CE times ED would equal AE times EB.
Yes. We can say CE times ED is equal to AE times EB. Right? So then we plug in, we get 6, CE is 6. 6 times 16 is equal to AE is 8 times EB, right? 8 times EB. And then, so that's going to be 8 EB equals 6 times 16. What's that? Middle math? Yes?
96.
96. Right, so then EB equals to what? 12. EB is 12. All right. Any questions on the notes? No questions on the notes. Very good.